This is the Math 2 Honors Unit 7C review. And number 1 asked, how do you find the period of a sine function in the form of y equals sine bx? Well, we know that the sine, or y equals sine x, has a period of 2 pi. So the difference now is if we have that b in front of the x. So what that b does is you just take the original period 2 pi of sine and divide it by b. And that's the new period. Number 2, describe the effect of m on the graph of y equals m times the sine of x. So normally that's what we call the amplitude. If we didn't have, usually if we just had y equals sine of x, it reaches a height of 1 and a depth of -1. But by multiplying by m, that becomes the new height and the new depth. So the amplitude will equal m, which means the maximum value is m and the minimum value will be -m. Could be a fraction, could be an integer, whatever m is. So on number 3 it says, what's the maximum value for the function y equals 7 sine x over 3? That 7 is the maximum. That's our amplitude. 4, what is the length of one period of the function negative cosine 2x? Well, cosine x has a period of 2 pi. But then you divide it by the number 2 here, which is in front of the x, so that reduces to pi. 5, what is the length of one period of the function 5 cosecant 3x? Cosecant also has, the basic cosecant function has a period of 2 pi. But that 3 in front of the x shrinks it down to 2 pi over 3. 6, what is the length of one period for the function secant pi over 5x? So the secant function normally has a period of 2 pi. But that pi over 5 changes it, and so we're going to divide 2 pi by pi over 5. In order to divide by a fraction, we're going to multiply 2 pi by the reciprocal of that fraction, which is 5 over pi. And this gives us 10 pi over pi, which reduces to 10. 7, where does the maximum or maximums occur in the first period for the function y equals negative cosine 2x? So I'm going to plot this. The cosine function starts high on the x-axis at usually a height of 1, but this thing has a negative sign, so it's actually flipped over, so it's actually going to start low and end low. So that's one period of the function. Typically it hits, if I just have y equals negative cosine x without the 2, it would hit its maximum at pi and end the period at 2 pi. But because that 2's there, we're going to divide these by 2. So we see there's only one maximum, and that happens at x equals pi over 2. Number 8, where does the minimum or minimums, or do the minimums occur in the first period of this function? I'm going to draw a little sketch of the function, or draw the first sketch, or the first period, starting at 0, 0. So typically, if this is just y equals 5 sine x, then some of the critical points, we got pi over 2 here, pi, 3 pi over 2. I wrote 3 over 2, let me fix that. And 2 pi. And that is just y equals 5 sine of x, but we want 5 sine of 3x. So that's gonna change the period of the function. What we end up doing is dividing all 3 of these by 3, or multiplying all 3 of them by 1/3. And so when we do that, we end up with pi over 6, pi over 3. This one's going to end up being 3 pi over 6, which is pi over 2, and 2 pi over 3. Okay, and so our minimum is happening at pi over 2. Alright, number 9, where does the 0, or where do the zeros occur in the function f of x equals cosine pi over x? So first, I'm going to start with y equals the cosine of x, focusing on where the zeros are. Cosine starts high, comes down, and ends high. This is in the first period of the function. And so this typically happens at pi over 2, pi, 3 pi over 2, and back up at 2 pi. Because we have cosine of pi over 5, what we end up doing is changing the period by multiplying all these numbers by 5. So pi over 2 becomes 5 pi over 2. This becomes 5 pi. Here we end up with 15 pi over 2. And here we end up, multiplied by 5, you end up 10 pi. So within the first period of that function, we have zeros. Zeros are where we cross the x-axis, happening at 5 pi over 2 and 15 pi over 2. Now number 9 doesn't say within the first period, it says in general, but I'm just answering this for the first period. Okay. Number 10, what are the excluded values for y equals 3 times the cosecant of x? So cosecant is the reciprocal of sine. And so to help us graph this, we can start with the sine function. So if I graph y equals 3 sine x, just the first period of it, it reaches a maximum height of 3, comes back down, reaches a min of -3, comes back up, and we continue doing that. The cosecant function is the reciprocal, so where there's the max opens up, whereas the min it opens down, and where sine is equal to 0 is where our function is undefined. So in the first period there's 2 spots, well actually 3 spots here. Okay, and so that's happening at 0, at pi, and at 2 pi. Okay, so again, highlighting, what's highlighted is the cosecant function, 3 cosecant x, and you can see the excluded values for x are 0, pi, and 2 pi. But this is asking what are the excluded y values? Okay, so this function will continue looking like that, back and forth. And there are certain y values that it won't hit. And those are the y values in between. So like the top part will hit all y values from 3 and above. The bottom part will hit all y values from -3 and below. I'm going to erase this helper sine function. There's this gap in between them in terms of y. And so what are the excluded y values? I'm going to write it out. All y values between -3 and 3. And another way to write that is -3 less than y, which is less than 3. Those are the excluded y values, everything in between them, not including them. Number 11, what are the excluded y values of -2 secant x? So let's get a graph of that. Secant is the reciprocal of cosine. So I'm going to get just a quick sketch of cosine that I will erase. Here's the cosine function. Wherever cosine is 0, it's where we get our vertical asymptotes. And then to, you know what, I messed up here because it's a -2 secant, so I need to flip this upside down. Have the negative cosine. And so now that's just my helper graph. My actual graph is what I'm doing in blue. hitting, this is 2, negative 2. And now I'm going to erase my helper graph. So there's the graph of y equals negative 2 secant x. And you see again there's this white space, this gap between the blue graphs, and that's between 2 and negative 2. So what are the excluded y values? The y values that are not included. All y values between negative 2 and 2. Okay, these are the y values that are not in the range of y equals negative 2 secant x. Because the range is all the y values that are part of that graph. So we found the y values that are not part of the graph. All right, 12, we're to find the amplitude and the period of this graph. The amplitude is equal to the number in front, 3 over 2. To find the period of the function, cosine has a period of 2 pi. So you start with that. But then we have this pi over 2, and so we're going to multiply 2 pi by the reciprocal of pi over 2, which is 2 over pi. And so when we do that, we end up with 4 pi over pi. Reduce that to 4. So we have a period of 4 and amplitude of 3 pi or 3 over 2. Number 13. In front of sine is a negative 1, so the amplitude, always positive, is equal to positive 1. The period of a basic sine function is 2 pi, but here we have the 2/5 here, so we're going to multiply 2 pi by the reciprocal, 5 over 2, and we end up with 10 pi over 2, which is 5 pi for our period. We're asked to sketch 2 periods of 2 times the cosecant of 2x. So to do this, let's decide where we want our 2 periods. I'm going to go from 0 to 2 pi. Sorry, 4 pi. And to help me with my graph, I'm going to first graph the sine, 2 periods of the sine. And I will be erasing this. That's 1 period, 2 periods. And hit our critical values. So we got 0, pi over 2, pi, 3 pi over 2, 2 pi. Keep going. So we're adding pi over 2 each time. This is 5 pi over 2, 6 pi over 2, which reduces to 3 pi, 7 pi over 2, and 8 pi over 2, which is 4 pi. We reach a max at 2, reach a min at negative 2. So right now I'm just graphing y equals 2 sine x, but now I want sine of 2x. So I'm going to multiply each of these numbers on the x-axis by the reciprocal of 2, which is 1/2. So pi over 2 becomes pi over 4. This is pi over 2, 3 pi over 4, 2 pi over 2, which is pi, 5 pi over 4, 3 pi over 2, cutting all these in half, 7 pi over 4, and 2 pi. Okay. Getting rid of the old values here. Then wherever the sine hits 0, that's where I'm going to put a vertical asymptote. Oops, that's not it. I'll clean that up in a second. And then draw the reciprocal. So the maximum, so we have a U shape here, we got a sad face here, smiley face here, sad face here, and then get rid of my sine function. And now we have our graph of 2 cosecant of 2x. There's 2 periods of it. We have all our critical x values that we need. We have our y values that we need. Everything's there. Okay, on to 15. We're going to sketch 2 periods of this negative secant 2 pi x. So to help us with that, we're going to graph y equals negative cosine of 2 pi x. Okay. So there's 1 period, 2 periods. And so we have 0. This is the basic cosine function. So first, y equals negative. I forgot the negative. Let's switch this around. So let's start again. Negative flips this upside down. So it looks like this. There's one period, 2 periods. So I'm going to put critical values on the x-axis. First of all, this is -1, this is +1 on the y-axis. We got for cosine x, for negative cosine x, this is pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, and 4 pi. Now I'm going to adjust this. Instead of y equals negative cosine x, I'm going to adjust it to y equals negative cosine 2 pi x by multiplying each of these by 1 over 2 pi, the reciprocal, or you can think of that as dividing by 2 pi. So if I multiply the first one by 1 over 2 pi, I get pi over 4 pi, which is 1/4. Next one, divide by 2 pi, and you get 1 over 2. Next one, you divide by 2 pi, you end up with 3 pi over 4 pi, which is 3/4. Divide by 2 pi, you get 1. So we already start to notice a pattern here. I'm going to clean this up. We're moving each critical point as a quarter, so 1/4, 2/4, which is a half, 3/4, 4/4, which is 1, and so we could just continue that pattern on. Uh, 3/4, 4/4, 5/4, 6/4, which reduces to 3/2, 7/4, and 8/4, which is 2. So now we have the numbers we need on the x-axis, we have the numbers we need on the y-axis. Now we are done with cosine as our helper function. We're ready finally to put on the secant, negative secant 2 pi x. So wherever that cosine function crosses 0, that's where we're going to put our vertical asymptotes. And wherever there's a maximum, that's where you put your smiley face. Wherever there's a minimum, sorry, that's where you got your frown. And we can get rid of our helper function here. And there it is. Y equals negative secant 2 pi x. (16) Sketch the following function with the appropriate restrictions. So we have our function here that we're graphing. Okay, that's a function we're graphing. And then the second piece here is telling us what part of the x-axis we want. So we want to make sure we're hitting from negative 3 pi over 2 to positive 3 pi over 2. So notice we're going as far left as we are on the left-hand side as we are on the right side. So here's what I'm going to do. I'm going to first, before I sketch in the details, I notice we're talking about sine, so I'm going to sketch one period of the sine function on the right-hand side. I may have to do less or more, I'm not sure. I'll adjust it later. And one period of the sine function on the left-hand side. Again, I'll make adjustments later. I should have looked earlier, but notice there's a negative sign, so I need to flip this upside down. So let's redo this. So flip the sine function upside down, one period upside down on the right-hand side, and one period continued on the left-hand side. Notice there's a 3 for the amplitude, so reaching a maximum height and a minimum height of 3 and negative 3. And first, with let's assume we just had the function y equals -3 sine x. So for the standard -3 sine x, we know we have it starts at 0, and on the x-axis we have pi over 2 for the minimum. Pi, it crosses at 0 again, max at 3 pi over 2, and 2 pi for a full period. Looking at just that right hand side, we're going to adjust those now to work with our function, which I'll put in blue, which is y equals -3 sine of 4x over 3, or that's the same thing as 4/3 x. So we multiply our pi over 2, pi, 3 pi over 2, and 2 pi by the reciprocal of 4/3. So when I take pi over 2 times 3/4, I get 3 pi over 8. When I take pi times 3/4, I get 3 pi over 4. 3 pi over 2 times 3/4 is 9 pi over 8. And 2 pi times 3/4 is 6 pi over 4, which reduces to 3 pi over 2. So now looking at what we have on the right hand side, our x value ends at 3 pi over 2, which is exactly what we wanted, because it says x has got to end at 3 pi over 2 up here, so that we have the right side completed. It's not too hard to fill in the left side, just put some negative values. So here max at -3 pi over 8, crosses 0 at -3 pi over 4, min at -9 pi over 8, and back at 0 at -3 pi over 2. So our x spans what we want, and everything we need is here. We have answered our question completely and got the graph where we want it. Alright, for number 17, we're looking at y equals 3/2 cosine 2 pi x, and we want to graph it for the range from -1 to 2. So to do this, I'm going to first ignore that range, and I'm just going to get a sketch of what y equals 3 over 2 cosine x looks like. And then I'll factor in that 2 pi and adjust the x-axis. So I start by drawing the basic cosine function shape. Start at your max, drop down to the min, back up to the maximum. We know that the amplitude is 3/2, so I mark 3/2 and -3/2 on the y-axis. And typically we have our key points at pi over 2, pi, 3 pi over 2, and 2 pi. And this is one typical period of the function. But we have that 2 pi in front of x, so what we're going to do is divide each of those x values by 2 pi. When I divide pi over 2 by 2 pi, that's the same as multiplying by 1 over 2 pi. I end up with pi over 4 pi, and that reduces to 1/4. So that I'm going to be replacing pi over 2 with 1/4. And then when I divide pi by 2 pi, that's going to reduce to 1/2. When I divide 3 pi over 2 by 2 pi, that gives me 3 pi over 4 pi, which reduces to 3/4. And then lastly, when I divide 2 pi by 2 pi, I end up with 1. So now I'm going to adjust the x scale. So our first x-intercept is at 1/4. Our minimum value is at 1/2. Our second x-intercept is at 3/4. Our maximum's at 1. So now I have the first period of our function graphed. Now I'm going to take a look at what range I need to graph this in. So the first period goes from 0 to 1. I need to graph this from -1 to 2. So if I because 1 is our period here, if I'm going to go to 2, I'm just going to repeat that cycle one more time. So that's at 2. Jump in by 1/4 each time. So here we have 5/4. Here's 6/4 or 3/2. Here's 7/4. And 2 is 8/4. And then we're going to go back a period as well. So -1/4, -1/2, -3/4, and ending at -1. So this is our graph of y equals 3/2 cosine 2 pi x, ranging from -1 all the way to 2. Number 18, we're asked to write the equation for each of the following trig functions based on the graph of its first period. It's not drawn exactly to scale. Okay. So on 18, we see that a few things here. We see that the amplitude is 7. We see that the period of this function is 3, because that's the length from -3 to 0 that we're given. Also, if I continue this pattern, it drops first and then rises. So this is the sine function, but it's flipped upside down. So I know that we're going to have something in the form y equals -7 sine. I'm going to put the letter b here for right now. We're going to figure out what number that is times x. And we also know that 2 pi divided by b is going to equal our period of the function, which is 3. So I can use that equation to solve for b. If I cross multiply, I get 3 times b is equal to 2 pi. Divide by 3 and you get b is 2 pi over 3. So plug that into our equation, and we were able to write the equation of our function, which is y is equal to -7 times the sine of 2 pi over 3 times x. Number 19, we have the basic cosine function shape. We have an amplitude of 4 and a period of, well, our x-intercepts are at 1/4 and 3/4 pi, so this is going to be pi, this will be pi over 2. So we have a period of pi. So we know that this is going to be y equals 4 times the cosine of b times x, where 2 pi over b is equal to our period, which is pi. We want to solve for b. We cross multiply and get pi times b is equal to 2 pi. Divide by pi, and you get b is 2 pi over pi, which is 2. Substitute that back in, and we have our equation. Y equals 4 cosine of 2x. Number 20, we're asked to write an equation for a trig function with the given characteristics. So it's got to be a sine curve with the amplitude of 4 and a period of 2 pi. So the typical period of a sine curve is 2 pi, and so this is just going to be y equals 4 sine x, because that has an amplitude of 4 and a period of 2 pi. Number 21, we want a secant curve with asymptotes at pi over 8 and 3 pi over 8 with a y-intercept at 0, 4. So to visualize this a little better, I'm going to sketch this because I think a visual is going to help out here. So y-intercept, well, first of all, let's get in mind what does the secant curve look like. The secant curve is the reciprocal of the cosine curve. The cosine curve, here's the basic cosine curve. And so the secant curve has vertical asymptotes wherever the cosine curve crosses, has an x-intercept. And it has, it looks something like this in green here. So I got the basic shape of the cosine function graphed here, and I'm going to erase the cosine function right here. So I got the secant function. And so now I'm going to put in a few things here. So first of all, notice we have a y-intercept at 0, 4. So the height here is at 4, which tells us that we have the equation y equals 4 times the secant of b times x. And we got to figure out what b is. We also know we have asymptotes at pi over 8. And another one at 3 pi over 8. Now the distance between asymptotes is half the period of the function. So I'm going to find the distance. So the distance between 3 pi over 8 and pi over 8, when I subtract those, I end up with 2 pi over 8, which is pi over 4. And that's half the period of our function. So if I double that, we have a period of pi over 4 times 2, which is 2 pi over 4 or pi over 2. Okay. So again, this comes from doubling the distance between the vertical asymptotes. And so I know that the typical period of a function is 2 pi. So this is equal to 2 pi over b. And I want to use this cross multiply to find out what b should equal. So I get pi times b is equal to 4 pi. Divide by pi, and you get b is equal to 4. So now I can write my equation, y equals 4 secant of 4b, or sorry, 4x. We need to simplify the expression using trigonometric identities. One technique that's helpful is to change or to rechange things into just terms of sine and cosine. And on number 22, we know that secant is the reciprocal of cosine, so I'm going to rewrite that as 1 over cosine x. And we still have times cosine, which ends up being cosine x divided by cosine x, which is equal to 1. 23, we have the cosine of theta times 1 over the cotangent of theta. 1 over cotangent theta, that's the cotangent's the reciprocal of tangent, so this is equal to cosine theta times tangent theta. Tangent is the sine over cosine, so this is cosine theta times sine theta divided by cosine theta. And then the cosines cancel out, and we just end up equaling sine of theta. We have 2 minus 2 sine squared theta. We're going to need to factor out a 2 first. So you get 2 times 1 minus sine squared theta over the tangent squared theta plus 1. Here we're going to have to use our trig identities to help us out a little bit. So what we do know is that so one of the basic trig identities is that sine squared theta plus cosine squared theta is equal to 1. And if I subtract sine squared theta from 1, I end up with cosine squared theta is equal to 1 minus sine squared theta. So I'm going to replace that 1 minus sine squared theta in my fraction with cosine squared theta. And we get 2 times the cosine squared theta Another trig identity is that the tangent squared theta plus 1 is equal to the secant squared theta. I'm going to erase that piece to create some more room. And now keep working through this. The secant is the reciprocal of cosine. So I'm going to split this up a little bit. We have 2 cosine squared theta times 1 over secant squared theta. And 1 over secant squared theta is cosine squared theta. So we get 2 cosine squared theta times cosine squared theta, which is 2 cosine to the 4th power of theta, because you get cosine squared times cosine squared, which is cosine to the 4th. 25. I'm going to distribute, and well, actually before I distribute, I'm going to check to see if there's any trig functions that might be helpful here. There's a trig identity. We know that tangent squared theta plus 1 is equal to secant squared theta. So if I change this around a little bit, and if I subtract secant squared theta, I get tangent squared theta plus 1 minus secant squared theta is equal to 0. and then subtract tangent squared, I get 1 minus secant squared theta is equal to negative tangent squared theta. So I'm starting with one of the trig identities and just changing the way it looks so that it matches what we have in our form here. So I'm going to replace the 1 minus secant squared theta with negative tangent squared theta. And I get cosine squared theta, or here it's x, I guess, times negative tangent squared x. Tangent is sine over cosine. So this is cosine squared x times negative sine squared x over cosine squared x. Let me delete some of this to get some more room. And we end up with, this is cosine squared x over 1, and the cosine squareds canceled out, and our answer is going to be negative sine squared x. (26) Notice we have two terms separated by a minus sign, and each term has a sine x. So I'm going to factor the sine x out. You get sine of x times 1 minus cosine squared of x. And we mentioned earlier that 1 minus cosine squared is equal to sine squared. We did that, let's see, back at 24. I'll highlight it right here. We had the 1 minus sine squared theta, and we changed it to cosine squared theta using the trig identity. So I'm going to use that again in 26, and I get sine of x times sine squared x, which is equal to sine cubed of x. (27) I'm going to just multiply out, and we get cosecant times cosecant is cosecant squared alpha. Cosecant times negative 1 is minus cosecant of alpha. 1 times cosecant of alpha is positive cosecant of alpha. And 1 times negative 1 is negative 1. The cosecant alpha, negative cosecant alpha, positive cosecant alpha, they cancel out. And you end up with the cosecant squared of alpha minus 1. And we have a trig identity involving cosecant squared, and that is that the cotangent squared of, I'll use alpha, plus 1 is equal to the cosecant squared of alpha. And if I subtract 1, I get the cotangent squared alpha is equal to the cosecant squared alpha minus 1, which is what we have, so we can change this now to cotangent squared alpha. Number 28, notice there's a 4 in each term, and we're going to have to factor that 4 out, and we're left with cosine squared theta plus sine squared theta, which from our trig identity is equal to 1. So this is 4 times 1, which is 4. 29. We have to use our cofunction identity because we have that pi over 2 minus x, and the cotangent of pi over 2 minus x is going to give us the tangent of x. Also, sine of negative x, we're going to have to use our even, odd functions here. Sine is an odd function, so sine of negative x is equal to negative sine of x. Tangent is sine over cosine, So we get sine x over cosine x, that's our tangent, divided by negative sine x. If you want, you could put that over 1. And whenever you divide by a fraction, you flip it over, so you get sine x over cosine x times 1 over negative sine x. Or we can make that a negative 1 over positive sine x. So the sine x's cancel out, and we end up with negative 1 over cosine x, which is negative secant x. All right, number 30, we have a trig identity that we want to prove. And so I'm going to rewrite it. I want to show that 1 minus cosine of x over the sine of x is equal to the cosecant of x minus the cotangent of x. Well, cosecant is 1 over the sine of x, and cotangent is cosine over sine. And you got a common denominator, and so when you subtract that, you end up with 1 minus cosine x over sine x, which is now exactly what we have on the left-hand side. And so there's our algebraic proof. Number 31. We want to show that this expression is equal to 1. So I'm going to change my tangent and my cotangent to in terms of sine and cosine. So we get sine theta times cosine theta times sine theta over cosine theta plus cosine theta over sine theta. And still we want to show that's equal to 1. Distribute the sine and cosine. So we get sine squared theta cosine theta over cosine theta plus cosine theta squared sine theta over sine theta. And we still want to show that's equal to 1. The cosine thetas cancel out, the sine thetas cancel out, and we end up with sine squared theta plus cosine squared theta is equal to 1. And that's a trig identity, so we end up with 1 equals 1, and that proves number 31. Number 32, I'm going to start with the left-hand side, and need a little more space here. Let me zoom in. So secant we know is 1 over cosine. Cosecant is 1 over sine. And I want to divide that by the cotangent, which is cosine over sine. Alright, still working on the left-hand side, so then that's going to be, the top part is going to be 1 over sine x cosine x, just multiply them together. They're still separate factors though. Times, I'm going to multiply by the reciprocal of the denominator, so you get sine x over cosine x. So when I multiply that together, the sines will cancel out, and we end up with 1 over, we got 2 cosines, so cosine squared x. And 1 over cosine is secant, so that's the secant squared x, which is what we were trying to show it was equal to. So there's our proof. I'm going to Distribute. Well, I'm going to change the tangent first to sine over cosine. So we got 1 plus sine squared w over cosine squared w times the cosine squared w. Distribute. Multiply everything by cosine squared w. You get cosine squared w plus the sine squared w times the cosine squared w over cosine squared w. Cosine squared w's cancel out, and now we have cosine squared w plus sine squared w, which by our Pythagorean identity is equal to 1, which is what we were trying to prove, and we have our trig proof there. 34. I'm going to work on the right hand side on this one. So I'm going to split it up to 1 over cosine x minus sine x cosine x over cosine x. 1 over cosine x is the secant x minus cosines cancel out. You get sine x. And that's exactly what we're trying to show it equal to, and our proof is done. The tide at a boat dock can be modeled by the equation y equals -2 cosine of pi over 6t, where t is the number of hours past noon. Y is the height of the tide in feet above the dock. What's the maximum height the tide will reach above the dock? So this is an amplitude question. Amplitude deals with the height, and here the amplitude is 2, which is the maximum height, and so that's our answer, 2. And then number 36, list all the excluded y values for the graph of y equals 3 sine x. So I'm going to sketch this graph. There's one period of that function, but it's going to continue. Okay, and so in terms of y values, this reaches a height of 3 and a depth of -3, and everything in between. So the included y values would be everything in between -3 and 3. So it would be from -3 less than or equal to y less than or equal to 3. So we're looking for the excluded values, though. The excluded values would be everything else. So we have two things. We have everything above 3, so y greater than 3, or we have everything below -3, y below -3. So that'd be a way to summarize all the excluded values for a function. And that concludes the review for our test.